All right, let's go ahead and get started. Welcome everybody to today's web seminar. The web seminar today is Solar Electric Investment Analysis, and we are funded through the North Central Region Sustainable Ag Research and Education Grant from the U.S. Department of Agriculture. And this particular grant is really focused on teaching what they're saying, train the trainers. It's professional development for people that are interacting with farmers with respect to solar. And this is one of the reasons that we're doing this web seminar for this particular group of people. And many of you are work with farmers in the rural banking sector, in the rural loan sector and other things like that. And when we've talked to groups like this before, there's been some interest in solar with respect to farmers are interested in wanting to talk more about it, whether that's about loans or just about the economics. And we're here to try to give you a little bit of knowledge and in-depth understanding of how to do those analysis so you can give better advice, or at the very least, have a little higher level discussions with those farmers. So welcome to our web seminar today. My name is John Hay. I'm an extension educator with the University of Nebraska at Lincoln, and I've been doing energy work for about 13 years here at the University of Nebraska, and I've been doing solar very heavily for the past 6 or 8 years. And in that time, I've done a lot of modeling, but also worked with an installer and installed about a dozen systems, including one on my own home that I did myself. But that's also given me a lot of experience with respect to the equipment and materials that are involved, and making sure that we're not missing anything when it comes to our modeling. Along with me here presenting, we're going to kind of co-present today, is Eric Romick from Ohio State, and I'll give him the mic to introduce himself.
Thanks, John. As John mentioned, my name's Eric Romick with Ohio State University Extension. I'm a statewide field specialist focusing on energy education. And I've also been, working with solar for the better part of the last 10 or 11 years. I do quite a bit of work both with the topic we're talking about today, so behind the meter, on-site or on-farm, I guess you would say, solar development. And also in 2008, I worked with our county commissioners and our economic development team, and was heavily involved with the development of an 85-acre utility scale project in my home county. So do quite a bit of work with solar, both utility scale and behind the meter. And just to echo John's comments, I've worked with farmers all across the state on this topic and this technology, and I am commonly either contacted by the farmer themselves, the lender, or their accountant. It seems like those are the three people that are most commonly trying to figure out, does this make economic sense? And the one thing that John and I've learned is the answer to that can be very complex, and oftentimes it takes a non-partial party to try and help understand, what are the best practices to conducting a financial analysis to just make a solid business decision. So that's our goal with this workshop series this month.
Great. I'm going to do the first half of today's session, and Eric's going to do the second half of today. But we are here for you and for your questions. And that's one of the reasons we do this live, is so that you're able to ask questions. So you have a chat box, and if you don't see it, you should be able to get to a menu at the top or bottom of your screen, depending on how you're set up. And there's a chat box. Go ahead and type that in to either directly to one of us or to the whole group, however you want to ask that question. And whoever's not presenting will be monitoring that, and we'll decide whether we want to answer that in real time or wait till the end, or for some simple questions we might just type in the answer in the chat box. So we'll be monitoring those as we go, so go ahead and ask questions whenever you feel like it, and we'll go in that way. Also, you can feel free to ask us questions on email at any time, and you can see our emails on the sheets here. So welcome. We're going to go ahead and get started. This is a 4-part series, so we're going to be presenting Tuesdays and Thursdays for the next 2 weeks at this time, 11:30 Central, 12:30 Eastern, and we used to teach this in 6, but we've kind of simplified it a little bit, and we're trying to get to all the component parts. And as we get further on, we're going to do more and more modeling and get into some of the detailed analysis that can be done, which might be of interest to you. We're going to focus today on 2 major components, and that is estimating system production and assessing system costs, which is really getting the groundwork we need to be able to evaluate a solar electric system. So this is kind of the what we're going to do today. We're going to talk a little bit about some basics, get into some production things, and then into some trends, and then finally kind of finish up with your questions and other things like that. When we think about production from solar, you know, one thing we can equate it to in our brains is simply something we think about a lot, or I think about a lot, which is what's the price of corn and how much are we going to grow this year? And so when we think about the economics of that corn crop, we're obviously interested in how much can we grow, but also in the price that we can get. Now, the price that we can get fluctuates sometimes very quickly, but lately it's been a little bit slow. So we can kind of have some plan, and we can actually forward market some of that and have a plan. But then the yield is maybe a little bit more variable. And so depending on the year, so there could be a year where we don't produce a lot, but have a high price and things are good, or the opposite is true. For solar, our yield is a little bit more stable. The production of electricity is a little bit more stable year to year. On a day to day, it's pretty variable, but on an annual basis, it's pretty stable. And that price, although is relatively stable, it varies quite a bit between utility to utility and state to state. And we're going to try to help you understand the value of that electricity starting on Thursday, actually. So, but we're going to talk about production today predominantly. I want to give just a little overview for anybody that's not familiar with solar. This also will give us a little bit of terminology when we think about pieces and parts of a system. When we think about the entire system, we're going to call that a solar array. And that could be the size for a house might be 10 or 15 panels, and it might be 50 to 150 or more if it's for a farm, a large farm. So the whole thing is going to be called the array. The individual solar panel, the industry calls a module. And I think that the term panel and module can be used interchangeably. The general public calls them solar panels. Again, if you're going to order one online, you look up solar modules, and that's what they're going to sell. Each solar module is made up of solar cells. Either 60 or 72 are the 2 common sizes. So a module might have 60 cells or 72 cells. One thing that's important to think about with this is when we think about Trump's tax credit that happened about a year ago on imported solar, he put a import tariff on imported solar modules and cells, but then they exempted a certain amount of cells from that tariff, so that some cells are coming into the country without tariff, because the modules are assembled in the United States. So there is a certain number of cells that came in without tariff, and so that's kind of where we can start to see the intricacies of that tax, import tariff. Inside that solar cell is a silicon crystal. There are a few other types of chemistries that are out there, but silicon is still the most predominant one. And inside that silicon crystal, we're going to create a electric field so that the electrons can go the proper direction. And they do that with just simple impurities of phosphorus and boron. And so we're going to put phosphorus in one layer and boron in another layer. And that creates a negative side and a positive side. And then those sides kind of pull on each other and end up swapping sides. But that centerpiece then we call the PN junction, or the positive negative junction. Now the electrons know which direction to go. They're going to flow towards the positive side because they're electrically negative. With the little wires, we can then catch those electrons, and if we throw in a photon, the electron gets excited, flows, gets caught in the wire, and gives us the electric current that is the electricity we're going to use. Though this is direct current electricity and not alternating current, and so we need some other component parts to do that. One of the things I like to tell, just for kind of maybe good trivia knowledge in the future, is that there's something else going on here, and that is the electrons in this case are flowing clockwise, and then these red things are flowing counterclockwise. These red things are actually holes, or what's the gap left by the electrons, but it's actually the holes that we describe as electric current. And when we label this electric current, we're going to actually label it and say that the electric current is traveling the counterclockwise. So that's the electricity is actually the holes. The electrons are flowing in the other direction. And there's a really important reason that we label it this way, and that is because Ben Franklin said so. And that's kind of a funny little thing to say, but what it is some scientists made an observation many years ago, and we have stuck with that convention to this day. And so the electricity is actually the holes that are moving, and not the electrons themselves. When we look at a solar panel, this is a spec sheet for a solar panel. And I really want to get to some very basic things about this spec sheet, not get into the details. But I highlighted in the upper left-hand corner the size of it. And what I'm really trying to get at is that almost all solar panels, at least the 60 cell panels, are almost exactly the same dimensions as one another. It's fairly standard in the industry. So if one breaks and you can't replace it with that same make and model, you can buy a different one, put it in, and it works pretty darn well. And I've actually replaced solar panels that got broken with rocks thrown from a lawnmower at one of our research farms with a different brand, and it worked just fine. And so the electronics don't care, but they do some nice things with respect to uniformity. The other thing is that when we talk about how much a solar panel or solar module can produce, we're almost always talking about it in standard test conditions. It's laboratory measured output. That's not the real world output. The real world output is less. So this is a 300 watt solar panel, and it actually is only 220 in real life. So we just need to recognize that when we're talking about it, we almost always label it under standard test conditions, but that's not the way it really works. It's actually going to be less than that. And we just base our actual calculations either on the real world numbers that they provide, or we make our own real world numbers, or the models do it for us. So we ought to be careful that to think it'll ever produce what it would in the lab, because real world conditions are always less. There's not a lot of stuff here other than we will say that they do increase in efficiency as it gets colder, and they decrease in efficiency as it gets warmer, but these aren't real significant changes. They're fairly minor. They're small enough that we really need to use those calculations for design purposes, but it doesn't necessarily affect us all that much in real life. Part of that, though, is the summer we may be a little less efficient, but we have more hours of sunlight, so it actually offsets and is better. I want to teach you a little back of the hand calculation, and you guys being kind of numbers people, you might appreciate this. I'm going to teach you a way to estimate how much a system can produce just by driving by the system. So you're going to drive by a solar array sometime here, and you're going to see it, and you're going to try to estimate how many solar panels there are. You just count them, or count up one side and the other, and figure out how many there are. And you're going to maybe multiply that number times 300, and then divide by 1,000, or multiply times 0.3, and that'll give you the kW rating of the system. So in this case, I'm estimating a 10 kW system. We're going to multiply that times the peak sun hours. So we have the standard test conditions capacity. We're going to multiply it by the peak sun hours, which you can either look up on this table, or in Nebraska, it's about 5, and really across the north central region, it's somewhere between like 4.7 and 5. So really estimating 5 is not too bad, but you could look it up on this table. We multiply that times 365 days a year, and then we derate it because remember, we're not in lab conditions. And so in this case, I'm going to derate it by 20%. So I simply took 10 kW times 5 times 365 times 0.8, and this system would generate 14,600 kilowatt hours a year. Let's do this for a real life system. Here's a system that we installed a year ago in July, and this has 48 solar modules or solar panels. If we multiply times 300 watts each, that's approximately the power output of many of these solar panels. And today you can get them higher or lower, but if we don't know, I like to estimate 300. So that's a 14,400 watts or 14.4 kW system. Here's my simple calculation: 5 hours, 365, derate by 20%. I get 21,000 kilowatt hours a year. That's my simple back the hand calculation, and I'm going to be within 5 or 6%. And the reason I like that is it kind of gives us just a talking point when you don't have any way to run a model quickly. It also gives you kind of a point at which if somebody's trying to tell me it's a lot more than that, I can kind of feel a little skeptical. And so it gives us a little bit of a double check. So another way to run this is to go online and run the PV watts calculator. This is a free calculator that the National Renewable Energy Lab has. And you simply put in your location and then put in the size of the system. You can make a few changes if you want, depending on if you know what tilt angle it is and what direction it faces and some of that. And you can make an estimate. So in this case, the solar PV watts model online from NREL estimated 21,208. Well, I'm feeling pretty good about my 21,000 now. That NREL is saying it's 21,208. And so we can compare those two pretty close. I actually called the installer that helped me with that installation, and he said that it generated 21,694 in the past calendar year. In its first year. And so we're feeling obviously pretty good about that. And I actually had both of those, truly, I had both those other numbers calculated before I added that third number today. So we're feeling pretty good about that. They're not always that close, but it does give us some pretty good back-end calculations to give us some estimates. And these models are pretty good. I just wanted to give a little bit of a picture of how these might be connected, particularly for this workshop, for this web seminar. We're interested in systems that are what we would call distributed generation systems or behind the meter systems. These would be systems that are connected to a home, a farm, a business. Obviously, we're thinking about farms a lot in our studies, but it could be a home, a farm, or a business. And so in this case, we would think about the solar sending electricity, and the electricity could go to the load, to the home, farm, or business. It could go to the grid if the home, farm, or business wasn't using it, or the grid can be used, and all three are happening kind of at any given moment in time. So we can think about where the electricity is flowing. That's generally how they're connected. The inverter labeled here is what the device that is turning our direct current electricity into the quality alternating current electricity that's needed for our homes and the grid. So it's making it grid quality, and it's seeing the electricity from the grid, so it's able to match it perfectly, and that's how it can match and be grid quality. If a person was interested in a backup system, they would need to include a battery and a charge controller, and then have a battery-based inverter. It's a little more complex. It's quite a lot more expensive, but you do not have backup with a solar array unless you have a battery. And we, in many cases, don't see very many batteries because of that additional cost, and it's probably not very cost-effective in many cases. But just need to know that if you want backup, you need that battery system. There's a couple different inverter setups, and I bring this up mainly because I want to introduce this to you before we get to Eric's presentation later, where he's going to talk more about costs. But the lowest cost setup is a string inverter. And a string inverter has one large inverter on a 1, 2, or 3, or maybe even 4 strings of solar panels. They are the lowest cost, which is quite a benefit. They do have some monitoring, so I can monitor them online, but I can usually only monitor them per string or for the whole system. I can't look at individual solar panels. They don't have good shade performance, which, if you don't put it in the shade, is perfectly fine. But they do have, but if you had a tree that shaded part of the system, you might lose the entire string. So in the case that I shade maybe half of this lower right-hand corner panel, I would lose the entire bottom row from production until that shade was gone. So they have poor shade performance. So if you have a shaded area, they don't work real well. So you want to consider your location for when you pick out your inverter setup. And the installers can help with that, but you want to tend to go to this because it's the lowest cost if you have an open area that doesn't have shade issues. It does require additional equipment for rapid shutdown. What they're basically saying is if you're going to put this type of system on a roof, you're going to need some additional equipment to meet the electric code. Microinverters are very popular today because they're very, very simple to install. But they are the highest cost. And in this case, I have a picture where the microinverters are individual inverters underneath the solar panels. They are the highest cost. You can monitor at the panel level so I can see what each solar panel is doing. They have good shade performance. If I have half shaded the lower right-hand corner solar panel, I'm only going to lose that one solar panel for production. Everything else is still functioning at full production. So it is good shade performance. It is rapid shutdown ready, means I can put it on a roof and meet the electric code just by design. They're very easy to install, and so that can help as well. And I know a number of installers that really like them, but many installers that I know really prefer them only on roofs because of the ease of installation and the rapid shutdown. They don't necessarily do them on ground mounts because of the extra cost. You can also be kind of halfway in between. This is a string inverter with an optimizer, which is can give us that shade performance that we want and give us the panel level monitoring. But what it has is 2 devices. Now, instead of installing just the microinverter or just a string inverter, you're actually kind of installing both. So the equipment costs are not very high, but your installation costs are a little more because you have kind of installation of both an optimizer, which is like a microinverter, and a string inverter. They can do panel level monitoring. They have good shade performance, and they're rapid shutdown ready. Rapid shutdown is not something we need to get into a lot of detail on. It is an electric code compliance issue, and is one that I like to ask the question of an installer if a system needs rapid shutdown, because I think that they need to be very well read on that particular topic. And if they can't rattle off an answer that is sufficient, I know that they're not well read on the electric code. And so meeting electric code requirements is really good. And that rapid shutdown question is a good one for that. Basically says for fire safety, we need to be able to shut them down at the panel level particularly when they're on a roof. So roof mounts need rapid shutdown, ground mounts don't. That's the general answer. It gets a little more complex, but that's the general answer. Not all systems are created equal. Which way they face, what tilt angle they're at can all influence production. And again, production is what we want. We need those kilowatt hours because that's how we're going to make money. So I have a couple systems here. There's a roof mount system and a ground mount system. You can tell that they're at different tilt angles. That's going to influence their production slightly. And so for the same size, the one on the right-hand side that's ground mount would produce a little bit more because it's at a more appropriate tilt angle for all year purposes. But we'll see how much less the one on the left will produce here in a little bit. But we can kind of compare those in that way. There's also ones that are a little unique. This one actually tracks the sun and will face the sun no matter where the sun is. And so it has a little sensor up at the top and it just looks at the sun and follows it. This system adds complexity, adds cost and maintenance, but this particular person wanted to try to maximize their production in their environment, and they have a lot of shade issues. So of all those solar panels we see in that particular picture, only 3 of them are actually producing at the moment this picture was taken, because of shade was causing loss of production on all but 3 of them. Also, temperature and tilt. Obviously, we talked about temperature. The warmer they are, the less efficient they are. So sometimes temperature can make a small impact. So open ones on ground mounts tend to keep cooler than ones against a roof. That doesn't mean a roof is a bad place. It's just one of those considerations. Of the 2 roof mounts on the right-hand side, you can see one of them changed the angle to try to gain some production. I would say in the current establishment or best practices for solar is I wouldn't do that. I would not change the tilt angle of my solar, because I'm adding costs of racking that I don't really want. Plus, in some ways, I'm also harming the aesthetics. Having it meet the same angle as the roof has a little better aesthetic than changing the angle. And the fact is that the solar panels are not a large piece of that cost of the system. They're a large piece, but they're not the largest cost of the system. And so in some ways, if we need a little bit more production, we get almost easier to add panels than it is to add all this expense in racking to change that tilt angle. One of the things, of all the things we talk about, one of the reason we talk about them is because obviously we're trying to help get good estimates and do good modeling. But also when a installer gives us a quote, they made a lot of assumptions on that quote, and we want you to be able to at least look through those assumptions or ask about those assumptions to make sure, are we on the same page? And one of them that sometimes gets missed is degradation, and that a solar panel degrades over time and produces less as the years go on. The sun degrades them. So but how much does it degrade them? That's part of the warranty structure of the solar panel, that they're warranted on a production warranty to the standard in the industry is effectively to produce 80% at year 25 of what they were when they were brand new. So if it was a 100 kW system when it was brand new, it's an 80 kW system when it's 25 years old. Now, there are a number of solar panels that have less degradation than that, and you can see that there's a few of them there. My estimate would not be to say, well, I want that LG solar panel or that Panasonic because it has less degradation. I really just need to account for that degradation in the system. The LG and the Panasonic are both very, very high quality solar panels, but they also might cost more to get that degradation. So if I'm running a Canadian solar that's only 82% guaranteed, it'll only degrade down to 82%. As long as I've kept that in my model standpoint from a degradation standpoint, it's going to calculate appropriately and it's going to work out. So we want to include that. There's a number of people that I've met that don't include that in their calculation, and that can be a problem. Let's talk about orientation for a little bit. This is just an example where a system was put at facing a different direction. So they said, well, I don't have a south facing roof. And remember, we want south facing because the sun is to the south of us. I don't need to go over the details of the sun's path through the sky, but generally because we're in the northern hemisphere, the sun is to the south of us in the winter, and it's almost directly overhead in the summer. So we want those solar panels facing to the south. If we were to face that panel to the east, we lose production compared to facing it south. And again, people will say, well, can I face it east or can I face it west? The answer is yes, but we want to model that production loss and make sure that we are estimating how much it's producing appropriately. In this case, we lost 13% by facing it east. I ran a model the other day and created this kind of temperature chart to show the tilt angle, and the direction it faces. So what we're looking at here is that in the middle is 180. That's facing 180 degrees south. And here these 100s are where we're within an error bar of getting 100% the maximum it can for the year, or the highest production annually it can. And so really a tilt for Lincoln, Nebraska, a tilt angle of right at about 40 degrees at facing 180 degrees south is our optimum. Now, a lot of people that we talk to, what's the appropriate tilt angle? We'll say, well, it's about 40 degrees for Nebraska. But the reality is you can do pretty darn well if you can get yourself within that box. And that means you need to face it generally south, within about 10 degrees of south. And you really generally want it somewhere between about a 25 and a 55-degree angle in Nebraska. If we modeled this in another location, it would be slightly different than this, but not a lot different. It would just be a little bit, it could be a little narrower, or a little wider. There's some, depending on where we're at. But generally, wherever we model, it's going to look a little bit like this. This little yellow box might move up or down slightly. So if we were to put this in Kansas, this yellow box would move down a little bit. If we were to put this in North Dakota, this yellow box would move up, you know, about 2 or 3 cells. And so that's kind of how that's going to work. And I really feel like if you can get within this larger yellow box, you're still going to feel pretty good. My system at my home is on a 412 pitch roof, which 412 pitch you can see on the left-hand side is about just over 18 degrees. And I'm facing south. I'm producing 94% of what I would if I had that optimal condition. But if I would have changed the pitch angle by just a little bit, I might have jumped to 96, maybe 97. To gain 3%, I would have spent quite a bit of money. So I left it at the pitch angle of the roof, and I recognize that I'm not perfectly optimum, but I'm doing pretty well. Again, and my models have proven out. I've been about 98% of what I modeled. So I modeled my output, and I'm right at about 98% of what I modeled. So I'm pretty close to that from a standpoint. I feel like I'm going to get my payback in about the proper time that I calculated. This is just another way to look at it, but I wanted to bring up those 2 trackers. The 2 trackers are simply one-axis tracking is I'm going to face east in the morning, and then through the day that tilts on one axis and it faces west in the afternoon. And so you can gain about 15% or maybe 20%, I think it's about 20% over a fixed system with a one-axis tracking. Though I also add maintenance and moving parts that can be a problem. So for most distributed systems, we don't see any tracking. But as we get into commercial and utility systems, very large systems, we add tracking. A lot of times the one-axis is the tracking that's added. The 2-axis tracks east and west, but also changes the tilt angle through the year. It's flatter in the summer and higher up in the winter. And again, adds a lot of complexity. And we don't see a lot of those 2-axis trackers because of cost and maintenance. So we see fixed systems almost exclusively for distributed systems. And then every now and then we see a one-axis tracking system for utility scale systems. That's becoming more common for large dozens and hundreds of acre systems. All right, I'm going to turn it over to Eric, and Eric's going to talk a little bit about system cost and how much these systems cost. And I'll switch over to the questions. So go ahead and keep asking your questions in the chat box, and we'll go from there.
You need to stop sharing your screen, John, and I'll pull up the slides on mine so I can advance them. All right, can you see my screen good?
I can, looks good.
Perfect. All right, so yeah, as John mentioned, we're going to talk a little bit about system cost in the second half of today's webinar. And as John talked about at the beginning, we used to kind of have a separate hour for each of these topics, but we're trying to kind of condense this part a little bit so we can spend some more time on the back end, really just getting into the model and helping you guys do some detailed modeling with a tool that's a free download that you can take back and use at your work. So I wanted to start out kind of just at a high level, and this is a question I've seen before from some farmers that had proposals, and they said, well, this is kind of really a no-brainer, right? But when you really get down into the details of these proposals, this tends to be the number that a lot of times they want to focus on. So installers really tend to lean on a simple payback calculation. And it's important to note that financial metric is really not the best metric to measure success in these projects for a number of reasons. As you think about variable rate structures on energy, it doesn't take into account the time value of money on a long-term investment, and so what we really need to be doing is asking less about what's the simple payback, and more about, well, what's the number we have to put on the check, right? So what is the initial investment that we're looking at here? And one of the things that I like to point out with this is there's so many variables just in this one example that really kind of dilute this simple payback. So first of all, if you kind of look up here, you can follow my cursor, they're assuming every unit of energy that they generate is worth 11 cents per kilowatt hour. And John and I are going to try and explain to you on Thursday and show why that's just not the case. It's a couple of other things that jump off the page at me here. Another thing we're assuming is that there's going to be a 10% electric rate escalation for 10 years. Which is fairly significant. We've not seen anything like that. National average real energy escalation rate, if you remove inflation, is around 0.5% annually. In Ohio, we're like 1.9%. Down here, they're assuming that a REAP grant is going to be funded, whereas this is a great program, Rural Energy for America program, and we'll discuss this a little bit on Thursday as well. In Ohio, at least, it's very competitive. So roughly 30 to 35% of the projects submitted in any given funding cycle are funded. So if it has to go in a bucket that's probable or not probable, it's not likely to be funded. And then this Invest Ohio tax credit program, this doesn't even qualify for solar. This is a job creation tax credit. And so, there's just a number of things in this proposal that can come up with this 2.6 years, but it's just not the best financial metric. The modeling tool that John and I are going to share with you, we really tend to focus on using multiple metrics. We like, first of all, making sure that we're discounting future cash flows and looking at net present value, looking at a discounted payback period, and utilizing levelized cost of energy to have all three of those help inform your decision. But back to this session here, we really want to focus on, okay, so $212,000 for a 50 kilowatt system, is that a good price? And what are we paying for? And that's what I'm hoping to help with here in the next few slides, is helping you to understand what is a good price for solar and what exactly are you paying for. So we tend to measure this and what's referred to as installation cost per DC watt. And what that's including is, it's kind of an all-inclusive flip the switch cost. Okay, that's saying, that takes into account the cost of the equipment, cost of labor, installation, net overhead, engineering, interconnection cost. That's a total flip the switch cost. And this chart is looking at it from the standpoint of residential, commercial, and this PV solar fixed tilt would be a utility scale system. Most of what we deal with in the agricultural sector kind of falls under this yellow bar. So we've seen basically a 77% decrease from $5.43 per DC watt in 2010 down to $1.83 per DC watt in 2018. So based on that proposal that I just shared with you in the previous slide, their cost per DC watt was $4.24 per DC watt. So, if we maybe step back and not focus as much on the 2.6 year payback period and focus more on what's the cost of the equipment that I'm purchasing. So those numbers that I just shared with you are produced by the National Renewable Energy Laboratory. They put out a quarterly report that analyzes PV system costs nationwide. And my experience here in Ohio has been that their numbers are really close to what I'm seeing in the field. So here's two examples of projects in Ohio that I've worked with. So one farm put a system in 2010, and it was a 51 kW system. Their install cost per DC watt was $5.98, compared to a system in 2016 that was installed at $1.85 per DC watt. So, we have seen significant decrease, both in the modeling cost that's observed by NREL, but also, what we're experiencing in the field here in Ohio. You will notice the actual payback period is longer, even though the price has come down. A big part of that is due to the changes in some of the grant funding. So Ohio had an advanced energy fund that it would actually fund up to 50% of a project. That program went away at the end of 2010 and no longer came back. And then the other thing was the value of renewable energy credits over time has really come down. And that's something else that we'll look at renewable energy credits on Thursday and look at some average cost of those credits as well. But if you're curious as to why, that's the reasoning there. But if, again, we kind of focus on this $5.98 and this $1.85, and then look back at that chart, you can see what we're seeing in the field is really close to what we're showing on the quarterly system cost analysis from NREL. So what's causing that cost to come down is the next logical question. And really the primary driver of the reduction in system cost has been the reduction in the actual module costs themselves. So if we look at this is the benchmark pricing for PV solar modules, you can see we've seen basically a 78% decrease from $2.23 in 2010 down to 36 cents per DC watt in 2018. So what that's saying is, I'm going to pull up a pie chart here. So remember, we were saying in 2018 it was $1.83 per DC watt was our total installation cost. Well, basically of that $1.83, 20% of that, or 36 cents, was allocated towards the actual purchase of modules. And this is a color-coded chart kind of showing the rest of that. You can see the inverter and balance of systems here. But it's important to note that basically, 59% or 60% of the total installation cost are based on soft cost. And so when we think about soft cost, again, that's 59%. And excuse me, I just had to admit someone else into the meeting room. So of that soft cost, 59% is going to be allocated towards installation, labor, sales tax, engineering, procurement, construction, just developer overhead and net profit. And so there's a significant portion of the installation that really has nothing to do with the actual equipment that you're purchasing. And so that's an important thing to keep in mind, because as you look at gathering quotes, a large part of those soft costs could be handled very differently from one developer to the other. So, we looked at the breakdown earlier and saw that 6% of the total installation cost was related to inverters, and John shared with us a number of different types of inverter technologies that we might consider for a number of different reasons. Part of it could be simplicity purposes in terms of installation. Part of it could be related to trying to qualify or be in compliance with Article 690.12 of the rapid shutdown standard, or it could simply be shading issues. So the reasoning for these different types of inverters are driven by a number of different factors, but you can see the cost is going to change. And John mentioned microinverters were the most expensive. You can see microinverters are actually 39 cents per DC watt if you break it down. And the 6% of the total installation cost for commercial systems was based on a 3-phase string inverter. So that number is based on this 13 cents per DC watt. But you can see that kind of gives you an idea of, how much does a DC optimizer add to the cost of the equipment versus a microinverter versus your string inverters. So, those are some of the cost trends for, the physical equipment, but there's all these other costs that we don't always know where to put them, but they certainly show up in a 25-year cash flow table. And so I think it's important to note, because, what John and I have experienced is you'll have some installers that are very detailed and transparent and do a good job of accounting for a lot of these other cost considerations, whereas others maybe not so much. And so it's important to make sure that you're comparing multiple quotes and really identifying what's included in those different quotes or proposals. So some of the other considerations you might think about, and these are all considerations that John and I will show you how simple it is to account for them using the system advisor model later on in this webinar series. But cost of capital, sales and property tax, insurance, operations and maintenance, inflation and discount rates, additional taxable income. So, if we're going to acquire a 25% grant, we need to account for that as taxable income in our cash flow table. And then reduction of tax deductible operating expenses. And this is one that isn't often thought about, but if you're generating your own electricity, then you're lowering the amount of electricity that your business is purchasing, and that you would otherwise have your kind of quote unquote write-offs tax season as a tax deductible operating expense. So I want to spend a couple slides just digging into a little bit of these other costs, and then we're going to take some questions. So as we think about sales and property tax incentives, I'm going to point to this desireusa.org website. It's operated with Department of Energy funding by North Carolina State University. This is an outstanding resource to look up state-specific solar incentives and policy. Basically, if you look nationwide, 25 states have some type of a sales tax exemption program, and 36 states have some type of a property tax exemption program. With that said, I like to remind folks that policy is complex and it's often fluid. So, even the best modeling job that we can do, there's still going to be a certain element of risk that lies within the ability of policy to change over time. As we think about a lesson learned, I was talking with a farmer from upstate New York, and he was really excited about his project. He had a 20 kW system that was installed, and he just loved it. It worked great. His net metering worked. He said the only problem is, he goes, it's never going to pay off properly or like we projected it to because of my property taxes. He said our property taxes went up $800 a year, and based on the system modeling, they were assuming that it was going to be exempt. So there was a statewide renewable energy exemption on property taxes in New York. However, that legislation changed, and there's actually a clause that allowed local municipalities to disallow that exemption. And his had done so, and they didn't check. And so I guess a lesson learned there is contact your county auditor or local tax assessor and just confirm, hey, we see, based on this legislation, we think we're exempt from property taxes. Can you confirm that, or can we get that in writing, just so that you don't have a similar experience as what the farmer did in upstate New York. Insurance is something that also is often overlooked. As we think about residential systems, a lot of times it's not as big of a deal. It's just kind of included under the homeowner's existing policy. Sometimes with commercial or farm systems, we see that, but oftentimes there's actually an additional cost that's associated with that coverage. However, we don't see issues like we did in 2008, 2009. there were actually some insurance companies that wouldn't insure them. And so, we had farms that were contacting other providers to actually get insurance. The problem with that is when they quoted covering the solar project, they wanted to quote insurance for the whole farm, and so that kind of naturally caused some competition. So the industry is kind of caught up, and it's not that big a deal to get insurance, but there is an additional cost oftentimes for farm systems. A general guide that we tend to use for modeling is anywhere from 0.25% to 0.5% annually of the total of the initial capital investment. And John and I got that number from a report through the National Renewable Energy Laboratory, as that was a guide they were using, and we kind of looked at that, and it worked. Also, I talked with a farmer that had a couple poultry barns, and they were looking at a 75 kilowatt system. And he also was in the insurance sector, so he sold insurance to the ag sector. And he mentioned, he said, we typically would do for a class 1 coverage on this. He said we would typically account for $5 per thousand of coverage. And so if you really think about it, it's just a clumsy way of saying 0.5% of the total capital investment. So that's a number that I'm pretty steady with as I do my modeling, is anywhere from 0.25% to 0.5%. So other ongoing annual expenses that you'll want to account for somehow is operations and maintenance. And this is just a picture showing that, while there's minimal moving parts and O&M coverage on solar is traditionally pretty low, there are things that happen, and there will be investments that need to be made over time. Here you can see we've had some wires that were rubbing on the racking and needed addressed. Combiner boxes and inverter boxes are a nice place for animals and rodents to kind of get up in there and chew or nest. Cable exposed to sunlight is prone to cracking over time. Some examples of water penetrating the actual seal of the modules. You can see here in the back side of the module, it's peeling away. So things will happen over time. A general guide that we use for O&M so that it shows up in a cash flow table is, it's been anywhere from $20 to $15 per kW annually. So it's based on the nameplate size of the system. We'll just assign a value. I tend to use $15. We can get really fancy with this, as John and I will show you next week, and actually do lower values and have, escalation above and beyond inflation that's allocated towards O&M costs. So we can get pretty detailed and tricky with how we handle O&M with our modeling, but it is something that needs addressed. As you look at kind of a commercial system here, and this is color coded, you can see, module cleaning, system inspection, and monitoring is a big part of it. That's, not replacing a physical component though. If we think about the components, the modules are very minimal, but we do see a fair amount of money allocated towards inverter replacement. And that tends to be the item that is most prone to failure. As you think about inverters and operations and maintenance, it is something that, just through regular O&M, you can increase the life of the inverter through making sure things are properly torqued and connections are properly, have the proper torque levels. Also cleaning the filters and just making sure that, through mowings and, dust and whether there will be animals in the area, just making sure that the filters are clean so the inverters are breathing properly and not becoming overheated or heat stressed. This is a chart that is just kind of putting some numbers to what would the replacement cost be. And so this would include both the purchasing of the equipment and installing it. So if we just looked at a simple string inverter on a 5 kW system, you're looking at $1,500 for the replacement of that 5 kW system. And then of course, as you get much larger systems, you could have larger cost allocated with that as well. Most inverters are warranted anywhere from 10 to 15 years now, and some inverters are actually, have a additional coverage that you can purchase to have that additional coverage of the systems. And so that's something that we can again build into that model so that it shows up in the cash flow table that way. So I want to kind of wrap up and get into questions here. Just in closing, not all systems are created equal. And if you can have one takeaway from the cost side of this discussion, I just encourage you to get multiple quotes. You know, if you have 2 or 3 quotes, it really helps kind of uncover anything that might not be accounted for or that might not make sense. So, if you have 3 quotes and they're all around $2 per DC watt, then that's probably a pretty good rate for that area and that size system. Whereas if you have one that's at $4.25 per DC watt and the other 2 are at $2, then that should kind of tell you that one's a little bit of an outlier. Some simple lessons learned: don't focus on simple payback calculations because there's too many variables that go into too many variables and assumptions that go into the modeling that can influence that. It's better to really focus initially on what's the number we have to put on the check. And if we're going to focus on financial metrics, let's look at net present value. Let's look at discounted payback period, levelized cost of energy. Identify the difference between systems because not all systems are created equal. As John pointed out, there's different warranties, there's different designs, different components that could be used. And then ask for farms that they've worked with in the past. Finally, in aggregate, a lot of these small details, it might seem like we're, really kind of splitting hairs and nitpicking on small things that don't have that big of an impact. And individually, that could be true. But, if you look at a proposal that does a very comprehensive job of including a lot of these real costs that your farmer or your business that you're lending to are likely to incur or will incur, it's important that, when you aggregate them, they do have a big impact. And so we need to account for them in our cash flow table. Finally, as we open this up for questions here, as we wrap up our first webinar, I just want to, again, introduce you to the System Advisor model. This is the tool this is a free download for anyone. It's developed with funding through the Department of Energy. You can go to the URL here at the bottom, sam.nrel.gov/download, and download that to your system. John and I will be giving you a crash course on this tool next week, but for anyone that has questions from clients that's looking for financing to fund renewable energy projects, specifically solar, this is a great tool that can really help you understand both the cost side, financial assumptions, system design, and production assumptions as well. And it does a really good job of bringing them all together. So I just kind of want to throw a plug out for that in case anyone wants to download it and play with it a little bit before we get together later in the week. So with that, this kind of concludes the first session of our four-part webinar. John and I, as John mentioned, we are recording these sessions. So we'll clean up the webinar recording here and distribute it to the email list for everyone that's registered. So you will get a copy of this in case you needed to reference anything. But at this point in time, John, let's go ahead and open it up to questions.